Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. In the previous sessions, we were talking about various sampling plans. Concepts of AOQ, AOQL, ATI, ASN were discussed in the previous sessions. To go ahead with this topic of sampling plan, in this session, we are going to work out a problem in plotting the OC, operating characteristic curve, and ATI, average total inspection, and AQL, average quality limit curves. Also, the values of average outgoing quality limit will be found out. So, in continuation with the talk about the topic of AOQL, determination of N and C was discussed in the previous session. If P is the incoming quality, there will be no defectives left in a lot of size capital N. If the sample contains more than C defectives, that is, there will be no defectives left in the lot of size N if the sample contains more than C defectives, that is, if X is greater than C. On the other hand, if X is less than C, that is, the number of defectives in a lot size of capital N is NP minus X. Thus, the mean value of the number of defectives after sampling inspection is given by M is equal to summation X is equal to 0 to C NP minus X G of X comma P. This G of X comma P is the hypergeometric distribution with parameters X and P plus summation X is equal to C plus 1 to capital N, the whole lot size, 0 into G of X comma P. Okay. So, in this sense, we will have a summation only X is equal to 0 to C, because this happens to be 0, NP minus X, and now just substitute for G of X comma P hypergeometric distribution, that is NP C X N minus NP C N minus X, the whole thing divided by NCN. Okay. So, the mean value of the fraction defective after inspection, that is AOQ is equal to P bar is equal to M divided by capital N is equal to summation X is equal to 0 to C P minus X by capital N NP C X N minus NP C N minus X divided by NCN. Okay. Now, subject to the variation in P, this P bar has a maximum value say PL bar, which is termed as AOQL. Now, this AOQL takes care of the consumer's interest because it is called consumer's risk. Given N and PL, that is the maximum value of P bar, PL bar, AOQL, the equation PC is equal to summation X is equal to 0 to C G of X comma PT is equal to all these this particular equation was discussed in the previous session. Just for recall, I am writing it here, NPCX NPT, this PT particularly, and N minus NP T C N minus X, the whole thing divided by NCN. Okay. Now, this equation contains two unknowns N and C. It is possible to select several pairs of values of N and C which will give P as defined in this AOQL formula. There are several values of small n and P, small n and C values which gives various values of P bar. As a safeguard to producer's interest, we select the pair which minimizes ATI as defined in ATI. All these has been discussed in the previous session. ATI is equal to small n plus capital N minus n into P. Now, the famous Dodge and Romick have prepared extensive AOQL tables for minimizing the values of N and C. Next, the OC curve for the incoming quality P is given by P A of P is equal to L of P is equal to summation x is equal to 0 to C G of x comma P, and this is equal to summation x is equal to 0 to C NPCX n minus NP C n minus x, the whole thing divided by NCN. When this P value is less than, we fix up a maximum value as 0.10. When P is less than 0.10, a good approximation to the PA of P, just written PA of P, and this is equal to summation x is equal to 0 to C NPCX n minus NP C n minus x, the whole thing divided by NCN is given by the first C plus 1 terms of the binomial expansion formula. The binomial expansion formula is given by 1 minus n by n plus small n by capital N whole power NP. Okay. It is actually 1 power NP. Adding and subtracting small n by capital N, we have this. Now, just bracket this and use the binomial formula, and we get L of P is equal to summation x is equal to 0 to C NP C x, then n by n whole power x, then 1 minus n by n whole power NP minus x. When P is less than 0.10 and also n by capital N is less than 0.10, a good approximation to this formula PA of P, just written this PA of P, this PA of P is given by Poisson's approximation. Actually, when P is less than 0.10, a good approximation to PA of P just shown is given by the Poisson distribution, with L of P is equal to summation x is equal to 0 to C e power minus NP NP power x by x factorial. Okay. Based on the discussions about OC, ATI, ASN, AOQ and AOQL, we will work out a problem in plotting the OC, ATI and AOQ curves, and from that curves we will extract the values of AOQL. Let us see this example. From a lot consisting of 2200 items, a sample of size 225 is taken. If it contains 14 or less defectives, the lot is accepted, otherwise it is rejected. So, plot the OC, ATI and AOQ curves, also obtain the values of AOQL. Here in this problem, we see the lot size capital N is equal to 2200, and from the lot of 2200, 225 items are chosen. Therefore, sample size is 225 and the maximum allowable limit, maximum allowable defectives is 14, isn't it? That is what is given. If it contains 14 or less defectives, the lot is accepted, in the sense the allowable defectives are 14, and from a lot of 2200, a sample of 225 is taken. Therefore, capital N is 2200, small n is 225 and C is equal to 14. Now, with this, using Poisson approximation to hypergeometric distribution, the OC curve, that is the probability of acceptance L of P or PA, is given by the formula L of P is equal to, just written in the Poisson's approximation to hypergeometric distribution, summation x is equal to 0 to c e power minus np whole power x by x factorial. Okay. And this is written as summation x is equal to 0 to c e power minus lambda power x by x factorial, where lambda is taken to be equal to np. Okay. Where lambda is equal to np and p is the submitted lot quality. This equation is marked as a star. The probabilities in star for different values of lambda and c can be obtained from the following table in biometrica tables for statisticians. Now, we compute this PA in the star for different values of P starting from 0 to 1. Now, the average total amount that is to be inspected under the above sampling rectification plan is given by ATI. ATI formula is n plus capital N minus n into 1 minus PA, and also from the previous equation we have AOQ is equal to P into PA. ATI is represented as star star and AOQ is represented as star star star. Okay. Now, we shall see this table. First of all, the p values. P values is given to be equal to, we will take the p values, so small p. P values is taken from 0.01 to 0.80. Okay, we are because we have assumed the p value is less than 0.10. Therefore, 0.10 means we can assume the values of p as 0.01, 0.02 etc. So, 0.01, 0.2, 0.3 etc. up to 0.08 and then 0.10 like that, and the above values of 0.10 of p is 0.30 is assumed and 0.80 is assumed. Now, with this we calculate lambda. Lambda is equal to n into p. N into p in the sense n is equal to 225, therefore 225 into p. Okay. So, this particular value 2.25 is obtained as 225 into 0.01. Then next is 225 into 0.02. Okay. The 225 into 0.01 is 2.25 and 225 into 0.02 is 4.50. Then we calculate the third tabular column. The third column stands for Poisson's approximation to hypergeometric distribution is e power minus lambda power x by x factorial. Okay. And here we have the first value to be equal to 0, and hence PA is equal to 1 because it represents the total probability, and then AOQ is equal to P into PA. P is 0.01 into 1, so that is 0.01. 0.01 into 1 is 0.01, and then n minus n into 1 minus PA, because we have a capital N is 2200 and a small n is 225 and PA is 1, therefore 1 minus 1, it happens to be 0 here. Next we have n plus n minus n into 1 minus PA. Since n minus n into 1 minus PA is this particular thing is 0 here for the first value, we have only n value, n is 225, therefore 225 plus 0 gives you 225. Okay. Next this value is e power minus lambda power x by x factorial. Okay. And x is ranging from 0 to 14, and here lambda value is 4.5. So, e power minus 4.5, 4.5 whole power 1 divided by 1 factorial is 0.000074, and then next PA value becomes according to the formula of PA, just summing it up to x is equal to 0 to C, we have 0.999926 and then just multiply this 0.999926 with 0.02, we get 0.01998 and then capital N minus N into 1 minus PA. Capital N, here PA value is 0.999926 and capital N minus N, capital N is 2200, this value is 2200 minus 225 into 1 minus 0.999926 and this value comes to be equal to 0.146150. Okay. And this value plus small n, because ATI is n plus this particular sixth column. So, 225 plus 0.146150 is 225.146. Okay. Then next, corresponding to P is equal to 0.03. This is 225 into 0.03 gives you 6.75. Just calculate e power minus lambda lambda power x by x factorial and then just add it, we get PA and then multiply it with the small p, 0.03 into 0.995566, we get PPA and accordingly calculate n minus n into 1 minus PA and then add it with 225, we get ATI. Now, with these values, we shall plot the OC curve, ATI curve and AOQ curve for the above sampling plan and it is drawn in the following figures as such. OC curve for single sampling plans. Okay. Here first of all we plot along x axis the p values. P values starting from 0.01, 0.02, 0.03 etc. up to 0.10, next to 0.30 and it goes on, just shrink the graph and 0.80 and on y axis you just draw L of P. L of P is equal to P into PA. Okay. And these values can be taken to be from 0.1, 0.2 etc. up to 0.9 and then 1.0. Okay. And like that for the first for corresponding to 0.01 we have PPA is 1, therefore the curve goes like this and just shrinks and get like this here. Okay. So, on x axis we have P and on y axis we have L of P, that is P into PA, and this particular curve is the OC curve for single sampling plan for the lot size capital N is equal to 2200 and small n is equal to 225 and C the maximum allowable limit of defectives is 14. Then next we shall draw the ATI curve, average total inspection curve for single sampling plans. Again P is taken as 0.02, 0.06, 0.08, 0.10 etc. It goes up to 0.40 and then the ATI values. You can see the ATI value starting from 200, 600, 1000, 800, then 1000. Likewise, it goes up to 2200 and 2600. Okay. And again this is the curve for the lot size 2200 and n is equal to 225 and C is equal to 14. This is the ATI curve for the single sampling plan for the lot size capital N is equal to 2200, n is equal to 25 and C is equal to 14. Next we shall draw the AOQ curve. AOQ curve again plot small p and AOQ curve and this is 0.02, 0.04 etc. up to 1.0 and then AOQ values are starting from 0.002, 0.006, next 0.008, likewise it goes up to 0.042. Okay. Just redraw the curve from this is 0.010. So, starting from here it reaches the maximum limit and then it comes down. When you plot the points you will see. So, you can see the maximum limit is the AOQL, average outgoing quality limit. We can see that as above 0.42. So, it is 0.046, somewhat like that. Okay. This is how AOQL is found out from the plotted AOQ curve. Similar example, plot the operating characteristic curve for single sampling plan where capital N is equal to 5000 and small n is equal to 100, sample size is 100 and C is equal to 1, 2, 3. Assuming PC is equal to 0.10, determine the LTPD that is lot tolerance proportion defective or fraction defective. For the above data, plot the average outgoing quality curve and determine the average outgoing quality limit. Since n by capital N small n is 100, 100 by 5000 gives you 1 by 50, 1 by 50 is less than 0.10. We can take the approximation to hypergeometric distribution as Poisson's approximation. So, the OC curve is given by L of P is equal to PA is equal to summation x is equal to 0 to C e power minus NP whole power m by m factorial, where P is the submitted lot quality and PA is computed from the biometrica tables, and also we have AOQ is equal to small p into capital N minus n by capital N into PA. Now, with these values we shall go ahead in calculating the ATI values from the table. So, NP is taken as 0.01, 0.20, 0.25 because n is equal to 100. We will take the values like this. 100 means 1, 2, 2.5, 3 like that we are taking. So, NP is taken here and then PA values for C is equal to 1, C is equal to 2, C is equal to 3 is separately taken from the biometrica tables, and then 100p into capital it's a multiplication 100p into capital N minus small n by capital N is calculated here. Capital N is 5000. So, 5000 minus 100 divided by 5000 into 100p. So, that gives you 0.01, 0.19 like that, and then using the formula of AOQ we will just calculate the AOQ percentage for C is equal to 1, 2, 3 and it happens to be 0.01, 0. Because what is AOQ formula, that is P into n minus n into capital N divided into PE. So, the percentage means this particular value into PE. So, 0.01 into 1 we get AOQ percentage as 0.01, and then similarly for C it is all 1, therefore, you cannot find out exactly what was the calculation done. Okay. So, the PA value for C is equal to 1 is 0.98 and 100p into n minus n by capital N is 0.19 and therefore, 0.98 into 0.19 they gives you the value 0.19. Okay. Similarly, 0.99 into 0.19 gives you 0.18. Like that the values are calculated for AOQ percentage. Now, we have the NP values starting from 0.01, 0.20, 0.25 etc. up to 7.7. Okay. Next, the OC curves and AOQ curves for different single sampling plans are drawn respectively, because we have 3 sampling plans corresponding to C is equal to 1, C is equal to 2 and C is equal to 3. All the things will be plotted in the same curve here, and this is 100 p values and this is p values 0.1, 0.2, 0.3 etc. it goes up to 1.0 and this is 0.2, 0.8, 1.4 like that, and the curves are drawn like this. This is for C is equal to 1. The next curve is for C is equal to 2, and the next curve is for C is equal to 3. So, the OC curves and AOQ curves for different sampling plans corresponding to C is equal to 1, 2, 3 are drawn for the lot size capital N is equal to 5000 and small n is equal to 100 and C is equal to 1, 2, 3. Next, we are also asked to find out the LTPD, that is LTFD, lot tolerance fraction defective. Sometimes it is also called as LTFD. It is same as LTPD, lot tolerance proportion defective. Now, for PC is equal to 0.10, from the above we have for C is equal to 1, we have LTFD value is 0.037. Okay. Draw a line parallel to the P axis at a distance PA is equal to 0.10 to determine the LTFD. Then draw perpendiculars to the P axis from the points where the line meets the OC curves for C is equal to 1, 2, 3. The abscissa of these perpendiculars will give the LTFD. Now, for P is equal to 0.10, from the above data we have C is equal to 1, LTFD is 0.037 and C is equal to 2, LTFD value is 0.0515. For C is equal to 3, we have again LTFD is 0.066. Now, based on the AOQ curves drawn on the plotted on the diagram, we have the AOQ limit for C is equal to 1 is 0.85 percentage, and for C is equal to 2, the AOQL percentage is 1.35 percentage, and C is equal to 3, the AOQL percentage is 1.8 percentage. In this session, we have plotted OC, AOQ and ATI curves with an illustration. Also, the value of AOQL from the curve was extracted. One more illustration was done wherein we have calculated the LTPD values by drawing OC and AQL curves. Based on the discussion in this session, the following questions may be posed. Draw OC, AOQ and ASN curves and also obtain AOQL values for the following sampling plan, where the lot size capital N is given to be equal to 2000 and the sample size is given to be equal to 150 and the allowable number of defectives is only 3. Another example is construct a single sampling plan for attributes given the following data. That is constructing the plan in the sense you have to find out the values of capital N, small n and C from the values given. That is AOQL is given to be equal to 0.05 and producer's risk is given to be equal to 0.05 and LTPD value is given to be equal to 0.20 and consumer's risk is 0.10. Thank you.